All right. Oops. So we had this guy, right? And
Yes.
Fam, were you able to get the structure, or what part of the structure were you able to get?
I don't understand about the charge -2.
Ah, okay. So
How can I put
the
this?
total valence electrons, right? From sulfur, how many do we have?
6.
From oxygen, how many do we have?
6.
So we have 4 times 6 electrons, gives us 24 electrons, right? But we have 2 extra charges on the molecule, meaning that we have 2 extra electrons.
Yeah.
So we have a total of 26 total valence electrons for this structure. Does that make sense?
Yes.
Cool. Sorry, that's really ugly. Do better. Right, so we've got our 3 oxygens placed around the sulfur. 2, 4, 6 electrons used in bonding. So we have 20 electrons left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20.
Yeah.
Okay with that?
Yes. Yeah.
Cool. So we've used all of our electrons. What's the next step we want to do? Anybody can chime in here.
Does it follow the octet rule?
Right. So the next thing we want to evaluate is do all of the atoms follow or satisfy the octet rule? So we look at each atom and how many electrons are around it, right, in the larger sense. So here our oxygen has 2, 4, 6, 8, right? This is 2 electrons per bond. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Right? So, octet rule satisfied. So this is a correct Lewis structure. Now, what's the next question we want to ask?
Whether if it has a polar bond?
Before we do polar bonds.
Oh, I see.
Yeah, we want to know if it has any formal charges. right? Everybody remember that part? Fan, are you tracking with me?
Yes.
Okay.
Okay.
So this is where I like to draw in all of the little electron boys. And this was another part of what Sadie was talking about earlier, where you see 3 lone pairs and a single bond on an oxygen. That is reliably a negative charge. Right? We can do the math on it still. We know that oxygen came to the table with 6 electrons, and it has 7 electrons here for a total of a -1.
Yeah.
Right? All of these oxygens have the same configuration of electrons, so all of them have negative charges. You still with me?
Yes.
Cool. So, how many electrons did sulfur come to the table with?
Right. +1.
What was that? I'm sorry.
+1.
So it's going to end up with a +1 charge, okay? Is everybody okay with that?
Yes.
So, is this structure charge minimized? Meaning, could there be less charges on this molecule?
Yes.
Yes, absolutely, right? So, how would we lessen the charges? What could we do?
You want to add a double bond to one of the oxygens.
Right, so we're going to take one of these lone pairs on the oxygens, doesn't matter which one we do, right? And we want to put it into a double bond. So, we get this structure. Once we change a structure, what do we need to do?
Recount your electrons.
Yes, so first thing we want to do is make sure we still have the correct number of electrons. We should have 26, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, right? So we're good on electrons. Sorry for putting extra dots in there. So what's the next thing?
You evaluate your formal charges.
Not yet. What's more important than formal charges?
Octet.
The octet rule, right? So we need to evaluate the octet rule. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, 10. Right? Is sulfur allowed to exceed?
Yes.
Yes, it is. Right? So sulfur is here. It is allowed to exceed the octet rule. So it is okay with having 10 electrons around it. So our octet are satisfied. Coolsies? Now what do we want to do?
Now it's the formal charges.
You got it. So this one didn't change. right? We still got a negative charge here, still got a negative charge here, right? But now that we added this double bond in here, we have 6 electrons around this oxygen, which is how many it came with. No charge. And we have 1, 2, 3, 4, 5, 6 around sulfur, right? So no charge there. That's your final guy.
Okay. Thank you.
Yeah. Does it make sense why? Are you comfortable with everything that we just did?
Yes.
Okay. What's the geometry of this bad mamma jamma?
Pyramidal.
Huh?
Trigonal pyramidal.
That's right. Trigonal pyramidal. Right? Do we have polar bonds? Yes, we do. Do we have asymmetry? So we have all the same attached atoms, right? So no asymmetry there. What's the other way that we can have asymmetry? Lone pairs. Exactly, Rochelle. Do we have lone pairs? We got a little lone pair right there, right? So we have asymmetry. Now, would we call this a polar molecule? This is where things get a little weird. Don't all chime in at once. It's okay to be wrong. Yeah. Is this a polar molecule?
I want to say no.
Why? Don't leave Carmen hanging here, you guys.
Is it because they all are satisfied with their, I don't know how to say it, they all equal their electrons, or?
So, I think what you're trying to say, Rochelle, is their dipoles are all canceling?
Yes.
Yes. That is not true because we have asymmetry, right?
Okay.
Right?
So it is non-polar?
So we have polar bonds and asymmetry.
Okay.
So that makes a polar molecule, right? Those are the two qualities we need for a polar molecule. You picking up what I'm laying down?
You kind of cut off for me. What was that?
So you have two qualities you need in order to qualify as a polar molecule, right? You must have polar bonds, and you must have asymmetry.
Okay. Do those two always go hand in hand, or can it be?
You can definitely have one and not the other, right? But if you don't have both of those, you don't have a polar molecule.
Okay.
Okay? Now, why is that a trick question? So, is this a polar molecule? Not really. And the reason being is because you have formal charges. right? What do we call this thing? What do we call this thing?
Sulfite?
Yeah, not the name, but what is it in terms of, is it a molecule? Is it an...
Covalent bond?
There are covalent bonds there, but I'm looking for a word that starts with an I.
Ionic?
Ion. It's an ion. It's an ion, right? So, if it's an ion, right, then we don't talk about whether it's polar, okay? Polar implies that we have unequal sharing of electrons, right? This is not just unequal electron sharing, right? We have ions here, right? That means that this thing is not going to behave polar, as a polar molecule would. It's going to behave like an ion. Right? So if you think of a polar molecule as having partial charges, right? Those partial charges will be attracted to other partial charges around them, right? That is an intermolecular force that's pretty strong. What do we call two polar bonds that are attracted to each other? What are the three types of intermolecular forces?
It's dipole-dipole, hydrogen bond, and dispersion.
Mm-hmm. So, if we have two dipoles, aka two polar molecules,
It's a dipole-dipole.
then we'd have dipole-dipole interactions. Those are relatively strong compared to dispersion, right? But ion with ion, now that's a full-fledged bond, right? If we have an ion hooking up with another ion, that is much stronger than an intermolecular force. Does that make sense? So in terms of relative strength, may I erase, guys?
Yes.
So in terms of relative strength, oops. Right, we have covalent bonds are the strongest. Sorry. Ionic bonds sorry. Right? These guys are the strongest. These guys are like glue, right? They stick atoms together to form molecules or compounds. Bye, Sadie. So, if these are the glue that stick atoms together to form molecules, IMF are like Velcro. All right? Not as strong as glue, but still sticky. Okay? The strongest of the IMFs is a hydrogen bond. Mm. Boop. The next strongest is dipole-dipole. Which is essentially just two polar molecules. Or more, right? And the weakest is dispersion. Okay? So, where these guys are gluing atoms together to form molecules or compounds, these guys are sticking molecules together to form solids. Whoops. And liquids, right? Dispersion forces being the weakest of them usually mean that you have a gas. Because there's not a lot of strength in the interaction between dispersion forces in molecules. So they're not very sticky, right? Not very sticky means that they're not going to condense into a liquid.
So, quick question for question number 2 on the homework. It says, which intermolecular forces are present in each of the following substances? A says nitrogen gas, and because it's a gas, would it be the dispersion?
Yes, absolutely.
Oh, you would just have to put dispersion?
Yep.
Oh, okay, cool. Thank you.
Yep. So, go through. So, looking at nitrogen gas is N2, right? Why is it N2? Why isn't it just nitrogen? Anybody?
I don't know.
Michelle? Why is it N2?
Well, nitrogen itself is a non-metal, but it's not a gas itself.
Oh, because it's a diatomic?
Correct.
Oh.
Correct. Have no fear of ice cold beer. Nitrogen is a diatomic. So, may I erase what's here?
Yeah.
Cool. Oops. Okay, this is nitrogen. Polar or non-polar molecule?
Non-polar.
Why?
Oh, did you say why?
Yeah, why?
No, sorry, I can't. Because you can't put the same. You can't. How do I word it? I have it right here. You can't bond to themselves.
They can bond to themselves, right? But when they're bonded to themselves, what does that mean? In terms of polarity.
Polar?
That's nonpolar, exactly, right? Is everybody comfortable with that? So if you have no polar bonds, then you definitely have a nonpolar molecule, right? So if this is nonpolar, then oops. Dispersion. Sorry. Whoops. So, can it have hydrogen bonds?
No.
Good guess. Yeah. So, these two guys require polar molecules. Okay? So, in order to have these two IMFs, one or the other of them, you have to have a polar molecule. This is the only one that a nonpolar molecule will have. If you only have dispersion forces, then your intermolecular forces are very weak, which means that you are probably a gas. Does that make sense?